A few notes about L'Hopital's rule. The first one here, and I hope you'll read it for yourself, but here's the key point. We have to make sure the conditions for using the rule are verified before we go ahead and use it. And you can be almost guaranteed that on a quiz or a test, I will definitely give you at least one limit where you don't need L'Hopital's rule. So make sure that the first thing you do, if you want to use L'Hopital's rule, is that it's appropriate to use it. And they give an example in your book where if you willy-nilly try to use it, you'll get the wrong answer if it's not appropriate to be used. So it only can be used if the conditions are met. The second note here is that we can use one-sided limits or infinite as x is approaching infinity or negative infinity, and L'Hopital's rule is still valid. And then the third note here is kind of interesting. This is sort of what we went over in the last video with the visual. When we have the particular case where f of a and g of a are both 0, f prime and g prime are continuous and g prime of a is not 0, then notice in this little algebra they work here, they're kind of going backwards. They're starting with the limit of the ratio of derivatives f prime of x over g prime of x. And they use direct substitution, and they let x be a. And then they have here the limit definition of the derivative for both f prime of a and g prime of a. So hopefully you haven't forgotten about that limit definition. It's nice to have it brought back again just as a reminder. So remember, the derivative is the limit of average rates of change. And then, of course, they're combining in this next step, using the limit laws, a ratio of limits to be the limit of the ratio. And then they're doing some algebra, and saying dividing by g of x minus g of a over x minus a is the same as multiplying by its reciprocal. So dividing by a fraction is the same as multiplying by its reciprocal. And then the x minus a's cancel out, and that's where they get to the next step of f of x minus f of a over g of x minus g of a. Taking the limit as x approaches a, now again, one of the things that this was premised on is that f of a and g of a are both 0, which winds us up with the limit of f over g as x approaches a. So again, it's kind of an interesting way they've shown it. They've started with the right-hand side of L'Hopital's rule and gone through these steps and wound up with the left-hand side. And as they mention here, the general version of the rule is more difficult, but that's okay. This is a good enough, gives us a good enough sense. Now, I strongly encourage you to read examples 1 through 5 in section 4.5 of your book. And we're going to start with exercise 7 from the exercises at the end of section 4.5. And notice we actually have a one-sided limit right here. So, of course, with any limit, as we learned in chapter 2, the first thing we're going to do is try direct substitution. So we have the limit as x approaches pi over 2 from the right of cos x, so I'm rewriting the question, over 1 minus sine x. So important to make sure you read that notation. The plus sign here is meaning approach from the right. It's nothing to do with the 1 minus sine x. Okay, so if we use direct substitution, we have the cosine of pi over 2 over 1 minus the sine of pi over 2, which is 0 over 1 minus 1, or 0 over 0, which gives us the indeterminate form, and that tells us, okay, it's okay to use L'Hopital's rule, which I will abbreviate L'H. So again, this is the kind of thing that you definitely want to show as part of your work. You don't want to just willy-nilly immediately start using L'Hopital's rule. You have to actually show why it's okay to use the rule. Okay, so now we're going to invoke the rule. We're going to rewrite the original limit, the limit as x approaches pi over 2 from the right of cos x over 1 minus sine x. And L'Hopital's rule says, because we got that indeterminate form of 0 over 0, instead of taking the original limit, we can take the limit of the ratio of derivatives. So the derivative of cosine x is negative sine x, and the derivative of 1 minus sine x is 0 minus cosine x. Okay, so the limit of the added constant 1 is 0. And of course, these minus signs I might as well turn into pluses. And now I can try direct substitution. And that is the sine of pi over 2 over the cosine of pi over 2. And that, in fact, is 1 over 0. Well, what should I do about that? This is not an indeterminate form where I can invoke L'Hopital's rule again. This is actually, how did I know it was negative infinity? I'll put a question mark there for now, but it looks like the limit doesn't exist. Well, one thing is, I could have noticed, if I were a little bit smarter, that at this point the limit as x approaches pi over 2 from the right of sine x over cos x is actually the limit of tan x as x approaches pi over 2 from the right. And I don't know if you remember what the graph of tan x looks like, but let's just do a little reminder here. Y equals tan x actually has a vertical asymptote at x equals pi over 2, and it looks something like this. So in fact, as x is approaching pi over 2 from the right-hand side, actually let me use another color for this. Here's x approaching pi over 2 from the right, and what's y doing? Oh yeah, it's going to negative infinity. So tan x, we say, is decreasing without bound as x approaches pi over 2 from the right. Right, so we might have noticed that a little bit sooner, but it's okay. The way we did it is fine as well. Now here's another thing. I would encourage you, since you have your calculator or computer with Mathematica, that you do a little technology check. Okay, and I don't know if you remember, pi over 2, that's roughly 1.57. Okay, it's an unending decimal, but for example, you could let x be 2, and then 1.75, and then 1.6, and then 1.59, and then 1.58. So you're letting x get closer and closer to pi over 2, or 1.57, from the right-hand side, and look at the values of tan x, and in fact, they do get more and more and more negative, or we say they decrease without bound. So the end result is that this original limit that we were given, we could say that the limit equals negative infinity, or, and I'm going to now erase the question mark, or we could say the limit does not exist.